Here in this video, we're going to look at the concavity of our graph. And concavity is talking about the way that your graph is curved. For example, if we look at the graph here, notice it is curved up, it's opening upwards, and that means that it is concave up, and then all of a sudden it switches to concave down where the graph is opening downwards. And this red point here is our point of inflection. And the point of inflection is where your graph changes concavity. And here it's changing from concave up to concave down. You will also note that if we were to draw our tangent lines to our graph, anywhere here where the graph is concave up, the tangent lines are below the graph. And when we switch over here and draw our tangent lines where the concavity is down, notice our tangent lines would fall above the graph. And that's always going to be true. Another thing you'll make note of is if you look at the derivative as we're concave up, your derivative will always be increasing. Okay? So your derivative is always going to be increasing, and then when we hit this point of inflection, we're now concave down. The first derivative here will always be decreasing as we go through the curve. Okay, so concavity looks at your curve being concave up or concave down, and the point of inflection is where our graph changes direction. Now, you also note that what's going to happen to the tangent at the point of inflection? Well, our tangent line would look something like this, and notice here at this point of inflection, our tangent line actually crosses through the graph, whereas where it's concave up and concave down, it just touches the graph. But at your point of inflection, your tangent line will actually cross through the graph. And you'll also make note, how can we determine our concavity? Well, this is going to be used with what's called the second derivative. And the second derivative, if the second derivative is greater than 0, it's going to be concave up. If the second derivative of your function is less than 0, it's going to be concave down. So if your second derivative is greater than 0, which means it's positive, it's going to open up, concave up. If the second derivative is negative, which is less than 0, it's going to be concave down. So let's look at an example of this here. Our first equation is y equals negative x cubed plus 3x squared minus 2. And this is going to be very similar to what we did with the first derivative test, except for now we're going to be taking the second derivative. And when we do that, we're actually going to find possible points of inflection. So we want to determine the concavity of our graph. So if we take the first derivative, we're going to get negative 3x squared plus 6x. Okay, and then we're going to take our second derivative, which would be negative 6x plus 6. And now this is going to be very similar to what we did before when we did that first derivative test, but now we're going to take the second derivative and set that equal to 0. And if we solve for x, we have negative 6x equals negative 6, x equals negative 1, and here, positive 1. If x is equal to a positive 1, this here is our possible point of inflection. So that is where our graph will possibly change concavity. So once again, that's going to divide us into two parts. If you look at your x-axis, we're going to have now two intervals that we need to test. We need to test to the left and to the right of 1. So that means we're going to look at negative infinity to 1, and then from 1 to positive infinity. And once again, we'll pick a test point. And if we're picking a point to the left of 1, I would simply pick 0. And to the right of 1, I would pick 2. Now we're going to take these points and we're going to evaluate those in the second derivative. So we plug 0 in for the second derivative, which is negative 6x plus 6, and we find out when we plug in a 0, it turns out to be positive, and if we evaluate the second derivative at 2, we end up with negative 12 plus 6, so that's going to be negative. Now, because our second derivative is positive, the conclusion that we can make here is that the graph is going to be concave up, and the graph then from 1 to infinity is negative, so that means it's going to be concave down. And if we go over here to the graph, we can actually look at this graph, and because we actually change directions from concave up to concave down, that tells us that this point here at 1 is actually a point of inflection. So at 1, which is right here, that's our point of inflection, and we can see that our graph actually changes from concave up to concave down. And again, this is using the second derivative to determine your concavity. All right, here we want to look at another example. F of x equals x cubed times x minus 4. And with this example, I actually want to look at two things. I want to look at finding where our graph is increasing and decreasing, and we can identify our relative max and relative min. And I also want to find our points of inflection if we have any. And that's going to be using this second derivative, whereas over here on the left for our critical numbers, we'll be using the first derivative. So for this one, I want to look at both to determine where our graph is increasing, decreasing, relative max and relative min. And then we want to find our points of inflection to find out where our graph is changing concavity. So first, we will look at calculating the first derivative. And I think here we could use the product rule, but to make it easier, let's rewrite this. Instead of taking the derivative this way, let's rewrite this. And let's first distribute the x cubed. So we would have x to the 4th minus 4x cubed. So now when we take the derivative, we would have 4x cubed minus 12x squared. So there's our first derivative, and like before, we're going to set that equal to 0, and we want to solve for x. So here we can factor out a 4x squared, and we will be left with x minus 3 equals 0. And if we set each of these equal to 0, 4x squared, set that equal to 0, we would have x equals 0. And then, of course, here we get x equals 3. So that's going to give us our critical numbers. And the other place we need to check is the derivative undefined? Well, no, this is a nice polynomial function, so it's defined everywhere. So the only critical numbers we have would be 0 and 3. So that means our test interval would then be negative infinity to 0, 0 to 3, and 3 to infinity. And then remember, we need to pick a test point. So I would pick from negative infinity to 0, I would simply use negative 1. 0 to 3, I would use 1. And 3 to infinity, I would use 4. So now we have to take our test points and plug those into the derivative, and realize this should be the first derivative here. So f prime of negative 1. If we plug in a negative 1, that turns out to be a negative sign. Again, we're plugging the negative 1 into the derivative here. And then we're going to take f prime of 1, plug 1 into the derivative up here, and we end up with a negative. And if we plug 4 into the derivative, we end up with a positive sign. So then our conclusion is that our graph at negative infinity to 0 would be decreasing, and from 0 to 3 it continues to decrease, and then from 3 to infinity our graph changes to increasing. So here we have our graph is decreasing, and then it continues to decrease, and then it is once again increasing. So from this we can conclude that at 3, at this point here, because it goes decrease and increase, this would give us a relative minimum point where x is 3, and then how do we find the y-coordinate? We plug the 3 into the original function, and if you do that you should end up with a negative 27. Okay, so that was using our first derivative test, and that allows us to determine where our graph is increasing and decreasing, and we can then identify any relative max or min points. And in this case we have one relative minimum at x equals 3. Alright, now if we go over here to the right, we want to look at how can we determine our concavity. Well, to determine concavity, then we need to look at the second derivative. So if we take the second derivative over here, we're going to end up with 12x squared minus 24x, and then we're going to set the second derivative equal to 0. So we can factor out a 12x, and we're left with x minus 2. And if we set each factor equal to 0, we're going to get x equals 0 and x equals a positive 2. Alright, so now, because this is the second derivative, these are possible points of inflection of 0 and 2. And once again, we're going to have our test intervals, which would go from negative infinity to 0, 0 to 2, and then from 2 to infinity. And then of course we need to pick a test point within the intervals, and I would probably pick negative 1, 1, and 3. And now we need to evaluate the test point at the second derivative. So now we're using the second derivative over here. So the second derivative evaluated at negative 1, that's going to be positive. And the second derivative evaluated at 1, if you plug 1 into the second derivative, it would turn out to be negative. And if we evaluate the second derivative at 3, if you plug 3 into the second derivative, it's going to be positive. So from this we can conclude with the second derivative, our function then is positive from negative infinity to 0. So our graph is going to be concave up. From 0 to 2 it's negative, so our graph is concave down. And then from 2 to infinity it's positive, so it is concave up. So that tells us that we have a point of inflection at x equals 0, because we're changing from concave up to concave down. And if it helps, you may think of it this way. Our graph is concave up, concave down, and then concave up. So we're going to have points of inflection where the concavity change, and that's going to occur at 0. Now, how do we find the y-coordinate? We plug 0 into the original function. If you plug 0 into the original, it's all going to cancel out, so we would end up with 0, 0. And when x is equal to 2, if you plug 2 in, you get a negative 16. So that tells us we have 2 points of inflection because our concavity changes twice. And here below, if we look at the graph, we can see how all of this is going to happen. We'll notice that at 3, -27, here we have a relative min, and then at 0, 0, we have a point of inflection. And then you'll notice also at 2, -16, and sometimes this could be hard to see, but actually right about in here you can see that we have another point of inflection. So our graph is changing here. It is concave up, concave down, and then it is concave up for the rest of the graph. So you can see the difference. With the first derivative, we can determine our graph is increasing and decreasing, and we notice that it is decreasing from -infinity to 3. So if we go from -infinity to 3, and 3 is here, our graph is decreasing. And then 3 to infinity, our graph is increasing. And then for the concavity, we can look at this and say, well, it's concave up from -infinity to 0. So notice from -infinity to 0 here is concave up. And then from 0 to 2, it's concave down. And then from 2 to infinity, it is continuously concave